Hey, so it's silly product review slash teardown hour here. What I have here, I don't know if you can make it out, but this is a, camera's being irritable at focusing, this is a Mega Power Company Blue Label USB precision soldering iron. That's right, what we have here is a USB powered soldering iron. Just because apparently somebody decided they needed to make one. I actually got this as a freebie from work. Surprisingly enough, it's actually usable. It's not a great soldering iron, but you know, considering the power limitations, you know, you can get 2.5 watts from USB. You know, 500 times, well, yeah, 500 milliamps times 5 volts, and it's 2.5 watts. I think it probably abuses your USB ports a little bit and draws more than that, and I'll check that out in a minute. But it's just a rather particularly amusing little oddment. I've actually used it to solder a little bit, and it, as I said, it's usable, if not a great tool. So here's the actual iron, so you can see it's just a little blue tube, and I don't know if you can make it out, but there's a little, like a cutout in the back of the, there it goes. You can see that there's a little cutout here, and that's the power button, so that turns it on and off, so it's a little toggle. There's the brand name. Oh, yeah. So there it goes. So you can see Mega Power Blue Label, blah blah blah. Heats up in less than 20 seconds. MSG 0885. So I'm actually probably going to do a teardown because I'm kind of curious, because looking into the, you know, looking in here, I can see that it looks like there is a single 14-pin SOIC package and then a couple little passes. Anyways, you can just see the back end is a micro USB port, and it comes with some amusing peripherals. It comes with, so yeah, I guess it does draw more current, because you can see we have one of these micro USB to 2 USB-A cords, so presumably that way it can draw 5 watts instead of 2.5 watts. And actually on the back of this it specifies current 800 milliamps, voltage 5 volts, power input 4 to 6 watts. So amusingly enough, you can also run it off of a 9 volt. So this is really a rather terrifyingly dangerous little bit of kit here. What we have here is it's a USB Mini B and a 9 volt battery clip. So I can easily see somebody doing some pretty horrendous stuff to a whole bunch of their USB peripherals by doing something stupid with this. But I guess the idea is that you can also run this off of a 9 volt battery. And presumably what would happen is it'll just draw so much current that the voltage of the 9 volt battery will drop to the point where it's within the range under which it can function. So, silliness abounds. And you can see it's got the little white LED is just in this tip right there, you can see it. So, let me really quickly, let's just measure the current draw. So, because I'm kind of lazy, I'm just going to use the readout here, so I need to put 10 turn pots on this thing. But anyways, so let me think. So this is going to be the negative, and that's going to be the positive. Oh, yeah. Shitty clippings are shitty. Oh, hey look, it just turned on. So, it's drawing 1.3 amps from my bench supply. So, I think their claim of 4 to 6 watts is kind of, well, that's 6.25, 6.5 amps. Or, excuse me, 6.25, 6.5 watts. So you can see the little lights on, and then you can see you've just got the little clicky button here. And it looks like the current draw drops basically to so close to zero that, or less than 10 milliamps with it off. That would actually be a fairly, I can't wire that up, it's a pain in the ass. Anyways, so if I let it warm up, it's quite a serviceable soldering iron. I mean, again, you have so little thermal mass there that it's not that usable, but it's, you know, if you need to make a quick joint in the field or something like that, it's definitely something you could get away with. Actually, one thing I wonder about is, it's possible they're doing some sensing about the source. So So let me, it's possible that, though I guess that seems a little excessively clever, that they know that, there's like a resistor in here that tells the soldering iron that it's connected to a 9 volt and can draw more current. I don't remember which is positive and which is negative. Ah well, if it's not reverse protected, it's shittily designed. So let's just have fun. Oh, I guess it isn't reverse protected. I may have just blown it away, blown it up. It's just drawing 2.5 amps. I think I've launched it. Oops. So apparently if you plug in the 9 volt battery backwards, it would self-destruct like I just had it do. Amused. Anyways, let me switch camera positions and we'll take a look at what's inside. So here it is. You can see that just a little tube, and you can see, I don't know if you can make out, there's definitely an SOIC part or something like that in there. Here's this hilarious 9 volt to micro USB, and then the USB cable sitting over there. So you can also see that there's just a little tactile switch in there, and then there's just a little section of bent housing. That's how the button works, and that's definitely warm. One thing is, if it's on for a while, this whole section gets quite hot. You can see that there's not a lot of heavy-duty insulation. You can also see that it's discolored at the tip quite noticeably. So that seems like it just pops off. It looks like there's a seam in there. I'm not sure if this was inserted this way or inserted that way for assembly. I think it was inserted this way. It's kind of interesting. It looks like if you look in there, let's see, where's my flashlight? So you can see like a pattern of horizontal lines in this direction, which is kind of interesting. I'm not sure what's going on there. Anyways, some sort of markings on the PCB, I would imagine. So, oops. Take my oldest pair of wire cutters. Oh, yeah. So the other thing I'm not too sure about is whether or not this has any sort of temperature sensing. And from what I've seen so far, I'm going to go on a limb and say, well, no, it does not. It's only got two wires going into the, two really fine wires going into the heater, which I just tore off. So there's no way it could, it's no temperature feedback. It's just going to basically dump heat in there. Unless there's like a cutout inside the element. So, okay, so I just need to grip that. Oh, I know what's going on, the switch is caught. So we can see a little more, there's a little label that says heater. Peel back the plastic. What is that? No, whatever's, it's quite stuck in there. Is it possible that this came out the other way? Fuck, yeah it does. So what I think I will do is, oops, yeah, there we are. So, there is our board. So the first thing of interest is here we have a little fuse. So you can see it's a... The first thing is you can see that there's a fuse here, marked 160, which I would imagine is 1.6 amps. So that is a limited efficacy considering that it drew 2.5 amps and blew out a lot of the internal stuff when I hooked it up backwards. You can see that we have one chip here, a little transistor, and then I would imagine that whatever that is, that's probably the main pass MOSFET. for switching the current. And then you can also see that we have, you know, basically one power rail along here and the other power rail along that edge. And then you can see that there's a resistor to this terminal, the LED, and in the other terminal and the other terminal, the heater are both connected there. So it's pretty obvious that they're just basically switching power to the heater on and off. Let's see if it's a little coming focus. So there you can kind of see the heater. You can also see Scene or Sean 9807/10. Could this have been designed in 1998? That seems pretty old. And then you can also see that there's a whole bunch of copper, this, you know, floating copper lands, and that's basically to just keep an even distribution of copper over the board. And it makes some of the processing easier and also saves on etchant. So it's a common, you know, kind of cost-saving mechanism. So I don't know why they left the silk screen off, maybe just because it looks cool. So the chip here is a 1406 or PAR 919. I'm not too certain. It's made by On Semi. So one thing that's quite interesting in this is it may have been hand soldered, but you can actually notice that there is no copper, or excuse me, no solder on many of these terminals. You can see that, where is my little pointer? So on all of these terminals along this edge, there is no solder, and these pins are effectively just kind of sitting there. Same is true for these 2 points right here. So I guess, you know, I'm not sure if they've left some stuff dangling or what, but that's kind of an interesting. You can also see that it looks like there's a capacitor, or that could be an upside down resistor. Pretty sure it's a capacitor. No, it says it's marked R3. So they either have upside down resistors or these are like unmarked resistors. That's quite interesting. I can also see some flux residue on the board surface. But there's a resistor going into presumably the base of this. I'm not sure if that's pulling up or pulling down. It may be a P&P pulling down or something like that. Because I would, well, okay, yeah, so it looks like there's a resistor here to pull this up. So I'm guessing that this is a P-type FET. So basically when they pull this lead here down, it turns on and it becomes a pass device. So that would mean that this would be an NPN transistor, and then this lead here is presumably going to the ground, so it probably runs under the chip to this leg here. Whereas here, this leg here just goes through the resistor and then that goes into the chip. So I would bet this is the base. So what happens is this chip drives this high, which pulls that low, which turns on the FET, which allows the whole circuit to work. And then you can just see that over here we have capacitor to ground and a resistor to the other leg of this. So I'm not too sure what's going on there. But you just got a little clicky button. So this is, I would guess this is a flip-flop of some sort. The other thing you can see is that this is a single layer board with only, everything's on one layer. There's no solder mask or silk or anything on the back side. So it's, you know, ultra budget. You can see that they're exploiting the, they're using the fuse to cross the traces over each other by treating it as a jumper. So here is the soldering tip. So I would, oh yeah. So I can't get this sucker out of here. So the issue is there's a lip here which is preventing it from sliding out of the housing. See if I can kind of abuse it a little bit. Why won't it slide out the other way? Oh, there's a lip back there too. Oh wait, there one. So here's the actual iron tip, and you can see that this is very thin-walled tubing. So this is basically going to have your thermal gradient across it. So I would guess that this is probably stainless, because stainless is, the thermal conductivity of stainless is very low, and also that way they wouldn't have to worry about rust. So there's a seam there, and I wonder if I can possibly horrifically abuse this a little bit. But maybe a little bit. Oh, hey, look, I see heater. So there's the actual heating element, and you can see that it's got, I would guess that that's nichrome wire. You can see the little tiny spiral in there. So the way most of these work, as I understand it, is they have like a high temperature, a high temperature conductive, or excuse me, a high temperature insulating powder, like made, a mineral powder. Generally, I think it's like alumina or something like that, or some other sort of, basically material like that. And then, so they have this carefully wire formed heating element, and then they basically insert it into the cavity that it's intended to heat, and then they fill it with this insulating powder. They kind of dump the powder in there and they vibrate it so that the powder settles very well, and then they basically seal it off. And that's how they make these high temperature heating elements, because the powder can basically, even if it's not very thermally conductive, the nichrome wire can get extremely hot, and that conducts the heat to the case, and yet it's insulative. The other option is they use like sheets of mica, but that's kind of another, that's also fiddly. And then you can see that it's extremely common. You can see how these are crimped, and the reason they do that is because, again, you can't really solder to nichrome. One, I believe it doesn't wet very well, so it's hard to get solder wetting on there, and two, the wire can get hot enough to liquefy the solder, so you'd have a bad connection. So by using a mechanical crimp, it's a much higher quality connection. And then I would guess what happened here is, this is basically, it looks like it's probably just a very thin tube. So they basically stuck the heating element wires in one end, and then you can see there's a little flat section. And then they stuck these two little wires from this heater in the other end, which are probably copper. These two fine wires here, I bet they're copper, tin plated or something like that, and they stuck those and they crimped them in the other end. And that's how you get the electrical connection between the two terminals. And then you can see that it looks like this may be a ceramic, I'm not too sure. One thing I could do that might help is if I use my old and very abused wire cutters, which I don't care about damaging. So you can see that it looks like the wire runs in the center and then coils out and back around the outside. You can also see that there's kind of like a white powder falling out. So the way I bet this is assembled is it looks like they have this, basically they make up this unit of these two, this little tip unit, which has the heating leads coming out of the back end. And then presumably they crimp the wires on, and then they thread this high temperature fiber insulating, tubes over it. And then I would imagine they press it into the end of this tube. They could also shove it in there and then spot weld it or something like that, I'm not too sure. But yeah, you can see how there's thermal discoloration as the, like the insulating material on there burns out. And then this is just a very piece of thin wall tube. And that just gives you a good amount of thermal resistance between the 2 points. So there's a hilarious little widget, and I will look up that chip and probably put the information in there. So just, freebie bit of work, really silly thing, usable in a pinch. Though, it also comes with, bonus for destroying your equipment. That just amuses the crap out of me. So this little board kind of piqued my curiosity. I was looking up the parts on it, and it turns out that this single chip on here it's an MC14106 Schmidt trigger. It's a hex Schmidt trigger. So it looks like what they're actually doing is they're really only using 2 of the 6 inverters, and the other 4 are these pads here, and then there are 3 along here. And they're taking advantage of the fact that they're Schmidt triggers, which means that the inputs are not extremely high impedance, which means they can be really lazy and just float the inputs and get away with it without the system kind of, self-destructing or oscillating continuously. So what I thought I would do is just doodle up this schematic. Let me find, there's my pen. Okay, I'm going to have to buzz this out, but I think I see how it's connected already. So basically, I don't know if it's probably not visible in here, but these 2 leads here are connected together. So you can see 1 and 2. So this is an input. This is an output. It's going into the next chain, which, so it's input, output, input, output. So together that's basically a unity. So what I will do, so one of the things you can do when you're in a situation where you need to get, fine access is you can, if you have like a dental pick or something like this, you can just put a clip lead onto it. The other thing you can do if you don't have one, is, assuming that your clip leads are of decent quality, you should just use that's going to be obnoxious, is to just use a pair of tweezers. So what I'm going to, that's very annoying. Oh yeah. So what I'm going to do, because I suspect that this lead here that's amazing, look at that. So if I poke this terminal with my diode checker, it turns on the white LED slightly. So between these two nodes is 0. So actually, so this should be a resistor. So that is reading as 100K. So it appears that they've got so here's the circuit. As you can see, it's extremely simple. So basically what's going on here is you can see that here's the push button. So what happens is basically this, you know, obviously you have a resistor here and this resistor charges this capacitor. So say that this input's low. You know, say that the system comes up. This is going to be low, which means this is going to go high. This is going to go low. And then that's going to feed back into there and keep this low. So this resistor could probably be removed, but it's a good idea to have it in there anyways. So, you know, basically just, so what's going to happen, this will be low, and then, but because this is high, this capacitor is going to charge up over time. And then what happens then is if you push this switch, well, obviously what's going to happen is this, you know, you're basically going to dump the charge of this capacitor into this node, which will, since this is high, it's going to drag this node up, which will hopefully cause this to flop over. This will be high, this will be low, and that'll stay high, and that will, you know, basically this node will then be high. So I would imagine actually what's happening is this resistor and this resistor basically form a divider. So I don't know what the value of this resistor is. Let me see if I can measure it. A lot of this, I'm performing these measurements in circuit. So I don't know necessarily how accurate they're going to be, because there's a lot of capacitors and, you know, active semiconductors in here. Yeah, that's not reading out right. But what I can say is that this is 100K. So my bet is that this is fairly large. You know, besides, you know, this is effectively going to debounce. You know, so this is going to form your debouncing circuit, the IC time constant here. So what's, you know, basically, so you push it and it'll change state, and then what happens is then this, you know, if this is charged, because it's going to drag this node up, and then for it to toggle again, it'll have to discharge this capacitor to this resistor, and then when you press it again, vice versa. That also explains why when you plug it in, it comes up powered on, because again, if this node is low, you know, I guess it could come up in either way. It's kind of, there's not a definitive power up mode for it. But anyway, so you just this feedback holds it in one state, and then the switch will always toggle it. So, and then you can see here's just the simple, I'm assuming this is a, you know, I'm assuming this is a transistor and that's a FET. They may both be FETs, they may both be transistors, so that strikes me as kind of unlikely. So what happens is you can see here that when this input's low, this is going to be high, or, oh, whoops, sorry, I drew this wrong. Yeah, that's another reason I think this is a FET. Bank is mailing me. So that's going to be like that, and then there's a resistor here. So what happens is when this transistor is off, this is pulled up, and that turns off the FET. I think I drew the FET backwards. I think this should actually be like that. Anyways, I never remember the hand-drawn symbols for FET MOSFETs, but it's whatever. So then what's going to happen is that when this transistor turns on, it pulls this down, which turns the FET on, and then you have current flow, you know, through the heater, which is the element here. So it's basically an inverter and a level shifter, and it has the advantage of that the FET's going to be fully saturated. The disadvantage is you need a P-channel FET, which are not as common. So again, this is this little device here. You know, this is the SOT23 part. There's this resistor here. One of the things that makes me fairly confident it's not a transistor is the fact that there's no resistor here. This transistor is connected straight up to this switching device. Then that would basically just blow the crap out of the base if this was an NPN a PNP transistor, because you'd need some sort of base current limiting. So the fact that, you know, you wouldn't for a MOSFET makes me think it's probably a FET. And then the other thing, of course, here is there's also just I may have the order wrong. Yeah, these are again backwards. It's the resistor and then the diode, but whatever. So then anyways, so, you know, and then you can kind of just see that they're only using 2 of these, and they just have it's an astable, I mean, it's stable in 2 possible states. And it's just a really cute little, you know, basically a way of implementing a flip-flop in the cheapest way possible. You know, and it also gets the bonus of the fact that it's all done with Schmidt triggers. So, because it's funny and I haven't played with it in a while, actually that's it. So obviously this cap is too small. So here's just a simple, you know, a cheap little simulation of how it works. So you can see we just have a push button, and you can see that, oops, basically just by connecting the push button, it toggles state. So you can also see that even if you hold the button down, it always flops into one state or the other. So a lot of this is going to be determined by some of the thresholds, but in any event, the silly little simulation. Oops. They need an interaction only mode. So anyways, the capacitor charges back and so forth. So there's just a fun little simulation of how it works.